All right, hello everyone. So this week we got two new functional groups that we're going to be learning about that are pretty similarly related. They have some differences. These are carboxylic acids as well as esters. We've talked a little bit about carboxylic acids before, but we really haven't talked about esters. So actually, let's start by just introducing carboxylic acids here. Carboxylic acids are when you have a carbonyl group and then a hydroxyl group directly connected to that carbonyl carbon, right? So remember we called this bond right here is a carbonyl bond, and now we have a hydroxyl or an alcohol group that's directly bound to this. So this whole chunk together is what's called a carboxylic acid group or a carboxyl group. So this is our new functional group that we're learning about here. In terms of how we name it, so we're going to be using the suffix oic acid to name our carboxylic acids, right? So if we have a one carbon carboxylic acid, if it was just an alkane, that would be methane. A one carbon carboxylic acid, we're going to replace the E with oic acid, so methanoic acid. Likewise, if it's two carbons, that would be ethanoic acid. Right, again, dropping that E and replacing it with this new suffix for carboxylic acids, oic acid. So again, that prefix, that metric prefix, as it always has, it really specifies the number of carbons, right? So when we have a one carbon, again, we sort of went over that, this is methanoic acid. What about when we have 1, 2, 3 carbons? That would be propanoic acid. If we had another substituent coming off of there, then we're going to have to include that in our name as well. We're going to start numbering from that carbonyl carbon. That carboxylic acid carbon is always going to be carbon 1 when we go about numbering our parent chain. So this would be 1, 2, 3. So now we have a methyl group located on carbon 2. So this would be 2-methyl propanoic acid. Okay, and notice how similar to when we were talking about aldehydes, right? That functional group, by definition of sort of how the functional group was, it had to be located on a terminal carbon. So we didn't have to bother specifying its location with a number. Notice with our carboxylic acids, we don't have to worry about it either. This is just propanoic acid, not one propanoic acid. We don't have to include that one on there. And that's because by nature of this carboxylic acid group, you have 1, 2, 3 carbon-oxygen bonds, which means that there can only be one carbon-carbon bond. So kind of like an aldehyde, it's always going to be located on a terminal carbon. It's always going to be located on carbon 1. So we don't have to specify its location with a number. Okay, like our other functional groups, we have to worry about the aromatic version, which always has its own special name. In this case, the aromatic version of our carboxylic acid is benzoic acid. And so when we go about naming these derivatives, we have to use that as our parent chain. So for example, here, this would be 3,4-dichloro because I got those two chlorine substituents. Benzoic acid as my parent chain. Likewise, this one, we're going to number from where that carboxylic acid group is. And so this would be 2-bromo benzoic acid. Okay. You know, in terms of the common names, it's sort of, you know, maybe worth noting, although I'm, as with all of our other functional groups before, I'm really going to stress more the IUPAC name. I do want to just sort of bring this up in case you see it on the ACS exam, God forbid. I'm hoping that, you know, if we have our IUPAC names down, we're going to be good. But just to note, so for the common names, the 4 smallest carboxylic acids kind of get their own weird thing. 1 carbon would be form, so formic acid would be methanoic acid. Acetic acid is 2 carbons, or ethanoic acid would be the IUPAC. Propionic acid is 3 carbons, or propanoic acid, and butyroic acid or butanoic acid would be 4 carbons, okay? So I'm really just gonna stress the IUPAC names, but it is sort of nice to, if you guys had that in the back of your mind, that would be great. The biggest one I think would be acetic acid is way, way, way more commonly used of a name than ethanoic acid. So if there's any one that you guys do remember, that one would be a good one. Okay, and we see these kind of in nature all the time, especially the smaller ones. Ethanoic acid or acetic acid, this is probably the most famous of all the carboxylic acids, and that's that sour taste that you get from vinegar. So vinegar, the main ingredient in vinegar is actually acetic acid. And if you've ever watched any cooking shows, or if you spend a lot of time in the kitchen, they'll talk about adding acid to a dish. And really what they're talking about are carboxylic acids, which are organically occurring acids that are found in foods. And they give it a sort of sour taste going on. So that kind of balances sweetness or fattiness or whatever. Another one, formic acid or methanoic acid, is that compound that irritates your skin when you get a bite by a red ant. So yeah, that kind of irritation feeling is from methanoic acid. Okay, so if we're going to go about giving IUPAC names for our carboxylic acids, again, sort of just as always, the step-by-step procedure is the same. It's just about learning that new suffix that we got, that oic acid. We got to find our parent chain, that longest continuous set of carbons. And again, I'm going to make sure to number starting at that functional group that, you know, we're interested in. In this case, it's the carboxylic acid group. So my parent chain would be the propanoic acid, right? My 3 carbon carboxylic acid. And then I have to include the 2-methyl at the beginning. So 2-methyl propanoic acid, and again, run that all together. That's all one word. I don't have to indicate the position of that carboxylic acid group. It's not 2-methyl 1-propanoic acid. It's just 2-methyl propanoic acid, because we're always going to assume that that carboxylic acid group is at carbon 1. All right, so just a few more examples. Again, let's find our parent chain, longest continuous set of carbons. So in this case, it would be these 4. Start numbering, again, going from that carboxylic acid group, 1, 2, 3, 4. So 3-methyl. And now we have a 4-carbon parent chain for our carboxylic acid. So that's butanoic acid. When we have a aromatic carboxylic acid, remember that we're going to consider this whole thing here to be our parent chain. And so our parent chain is the benzoic acid. Now we got to include the substituent. Again, we're going to start numbering from that carboxylic acid group. So this is 3-bromo benzoic acid. And if we wanted to go the other way, let's draw the line angle formula for 4-chlorohexanoic acid. Going the other way, let's just sort of pick this apart. I like to identify the parent chain first. So that's going to be the hexanoic acid. And then we're going to make sure to include the substituent chlorine on that 4th position. So let's get our parent chain down first. Oops, 1, 2, 3, 4, 5, 6. Can stick that carboxylic acid group on that 1st carbon. So this is carbon 1, 2, 3, 4, 5, 6. So then on carbon 4, we're going to need to put our chloro group. Okay, and I think by now you guys are pretty well versed in the bond line structures versus the condensed structural formula, because that's something that we've been drilling pretty heavy since the beginning of the semester. Okay, in terms of how we prepare carboxylic acids, this is actually one of the things that we discussed before when we were talking about first alcohols and then aldehydes, right? Alcohols can be, let's just actually label these. Alcohols can be oxidized to aldehydes, which can be further oxidized to our carboxylic acids. Okay. So that's the way that we can prepare carboxylic acids from either primary alcohols or aldehydes. There is in terms of biochemistry, there's one class of carboxylic acids that tend to be particularly important, and these are called alpha-hydroxy acids. They're found in fruit as well as milk, sugarcane, and these are carboxylic acids. Again, they're naturally occurring, and they have a hydroxyl group on the carbon atom that is adjacent to the carboxylic acid group. So what do I mean by that? That means if I have a carboxylic acid group, a hydroxy acid, an alpha hydroxy acid, has a hydroxyl group or an OH group located on the carbon right next door, right? So however big or small this parent chain on the back is, whatever shape it is, doesn't matter. If I have an alcohol group or a hydroxy group located right next door to an carboxylic acid group, this is going to be considered an alpha hydroxy acid. So some big ones would be the glycolic acid, which is found in sugarcane, lactic acid, which is both kind of what that sour milk taste is, but also what builds up in your muscles after you work out. That's an alpha hydroxy acid. Tartaric acid, which is something that's found in the skin of grapes. It's a big component of wine. Malic acid from apples, as well as citric acid, which is of course in all of our citrus fruits. These are all examples of alpha hydroxy acid. So just an important commonly occurring carboxylic acid.